Welcome to Essential Problems with CRIP. This video will primarily focus on polyatomic ions and rationalizing the trends on the periodic table in order to adequately memorize them, as well as writing formulas and names for common ionic compounds with polyatomic ions. So let's begin. I'm going to take a series of polyatomic ions just so for you to see the trend. So ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. If you notice, all of the polyatomic ions going down from all the with chloride, with a bromide, with iodide, you could all have this kind of set in which they will all have a negative charge. And so honestly, if I drew them out really quickly, again, you should get used to the method of drawing polyatomic ions, but I'm so used to this that I can just go ahead and draw them quickly. Because definitely you begin to see a pattern when you draw these. And maybe, again, you need to know how to draw polyatomic ions before you do this. But once you start to see the pattern, it actually helps to remember these too. Because if you notice, there's always going to be one of the oxygens that have a negative charge. And you should get comfortable with why. Because chlorine, again, has no formal charge because 1, 2, 3, 4, 5, 6, 7, right, electrons around it in each case. And so therefore, in this last one, we can also draw this real quick. That's a sloppy tetrahedral, but whatever. Okay, so in all of these cases, and that goes for all of the halogens, when they form polyatomic ions with oxygen, you have either 1, 2, 3, or 4 oxygens, and you will always have this one negative charge. And in order to name these, right, it's different from the other ones where you typically only have 2 to choose from. And so typically, so if there's only 2 to choose from, right, it's easier to name. And this is the same idea though. All of the smaller ones will end in "ite." Okay, so that's just a Latin word forming suffix to indicate that it's smaller, right? Versus 8 is larger. Okay, and so you can just remember that by 8 is great and ite is slight. And, well, how do we distinguish the smaller ones, right? These 2 smaller ones from the 2 larger ones? Well, then we add a prefix here. And per just means derived from. Dear Lord. Per means derived from. And that's going to be associated with our larger one. Hypo means under, and so that makes sense. So we're not saying hyper, but you got a per there. So not hyper, but just per, right? And hyper, of course, means above. Here, per just means derived from. So it's kind of similar type of thing. Hypo, under, so smaller, underite, right? So we say hypochlorite, chlorite, chlorate, perchlorate ion. Now, the other substances on the periodic table are kind of easier because they typically just come in pairs, so not in groups of 4, but in pairs. And you can see a distinct trend. So if we look just to the left, right? So here are the halogens on the periodic table. You have all 1 negative. Well, if we look just to the left, say, take stuff like with sulfur, right? So SO3, 2 negative, and SO4, 2 negative, right? Sulfite, this will end in ite, and this will end in ate. Forgive the fire alarm in the background. It's like World War II era. So here we have sulfite and sulfate, right? And notice, again, both of these are 2 negative. And that really matches, if you will, right? sulfides ionic charge. Just like these guys match chlorides ionic charge. So it's very easy to remember once you make that connection, right? That these will always be two negative. And really, the distinction between them is that we have three oxygens, that's the smaller one, four oxygens, that's the larger one. And so we can, begin to see, and any ions that are in that group are going to follow that pattern, right? So you have sulfite, sulfate. We can have selenite and selenate, etc. And you're going to see the similar type of pattern in which for sulfur, right, you're going to have actually two oxygen atoms that have that negative charge, and there'll be one double bonded here, right? And same thing with the sulfate. So honestly, again, you should know how to draw them well, but it's almost as if once you start drawing them well, you realize that the formula and charge is almost kind of telling you the structure a bit. And you can check that, and you'd see that, if we count total valence electrons, oxygen has 6 times 4, 24, 24 plus the 6 from sulfur is 30, plus the 2 negative charges, 32. And you can see right here, we've got 32 valence electrons on all the structures, right? Of course, these two will have a formal charge of 0. This will have a negative charge, and the sulfur has a formal charge of 0. Notice you are able to have an expanded octet because we are in the third energy level, not in the second energy level. If we're having a second energy level element, right, we wouldn't be able to draw this structure. Okay, let's go one more. So here we have hypochlorite, chlorite, chlorate, perchlorate. Here we have sulfite and sulfate, right? Well, if we go over a bit, we can get to, say, phosphite. So PO3, 3 minus. And phosphate, PO4, 3 minus. So again, this is the ite, the smaller one. And this is the 8, the larger one. Right? And again, it's going to follow that trend, and you can kind of envision the lone atom, the monoatomic ion of phosphorus, as having the same charge as these guys. And again, there's going to be a similar dynamic here. So phosphorus would have, in phosphite, 3 oxygens with a negative charge. And you would have an unshared pair remaining, and that would have to be on the central phosphorus. Here for our phosphate, and there we go. Okay, so and that's the general trend that would that will help you to really memorize these polyatomic ions. That really takes care of most of them. Of course, the pattern is a little bit different for the second energy level elements. So let's look at those. So the pattern is different because those second energy level elements are substantially smaller. You don't have an expanded octet. So we have a different trend that takes place, right? So you can kind of see in relation to oxygen, everything's, in relation to oxygen here. You can kind of think of it, the pattern, as being a bit different once you, are next to that oxygen. So we can look at nitrogen, right? And we've got not NO3 and NO4, no, because it's too small. Nitrogen's too small. So I actually have NO2 and NO3. And notice the charge also kind of resets here. The total charge is negative, right? And versus carbon 8. And actually, carbonite is possible. So, thinking like Star Wars, but it's just not, it's very unstable and breaks down. But at really super cold, 2 minus, sorry. At super cold temperatures, you can get carbonite to occur. But notice the naming scheme is the same. So the smaller is eit, and the larger is 8. Of course, the thing that we need to keep in mind is we don't have O3 and O4, we've got O2 and O3, right? And the structures are also going to have this kind of similarity to each other. So let's draw nitrite. So nitrogen, right? And one of the oxygens will have a negative charge, and the other one will have that double bond. Of course, there would be one electron pair remaining. And again, you can count total valence electrons, and if you place it systematically, like in the previous video, that's exactly what you should end up with. You should not memorize just the structure itself. That's ineffective. You should get so used to drawing the Lewis structures that you really are intimately understanding what's going on. So for instance, you might be inclined to do a significant error here. So what do I mean? A lot of students, when they draw nitrate, they draw nitrogen, right? And they immediately do double bonded oxygen, and single bond with a negative charge. That's what they do, right? That is completely wrong. That's completely wrong. Why is that completely wrong? No, don't ever do that. Why is that wrong? Look at nitrogen carefully. You've got actually nitrogen breaking the octet rule, and you have to really, really put this ingrained in your mind. Second energy levels second energy level elements cannot break the octet rule. So this structure is completely wrong. The correct way to draw nitrate is actually following your method, right? If you begin drawing this correctly, this is how it should be begun, just like carbonate, right? And the nitrogen should be assigned a 2+ charge. Notice 6 times 3, 18, 18 plus 5 electrons, right? And another one here, so 6, so 18 plus 6, 24. This has the same total valence electrons as carbonate that we drew, right? If I, just for sake of comparison in structure, I can draw carbonate, and in the previous video, if you recall, at this point, I had drawn that. Notice it had a positive charge. Here I have a 2+ charge because it only has 1, 2, 3 valence electrons directly on it, whereas it should have 5. And here this has 3 valence electrons directly on it, whereas it should have 4. So notice the similarity. Of course, I was able to form 1 pi bond. I can only form 1 pi bond here as well, or else I would break the octet rule. So actually, the complete structure for our nitrate is nitrogen in the center, right? Negative charge, and a double bonded oxygen there. And in the center, nitrogen will have still a +1 formal charge. Now you say, well, that doesn't look nice. Well, deal with it. That actually helps to describe nitrates, right? That kind of stability inside the bonds, and as far as the placement of charges. And really, if we were to draw nitro groups, which a nitro group is just like this, the nitrogen attached to a carbon. And nitro groups are definitely distinctly unstable. Nitro groups are commonly found in explosives. They're all riddled all around explosives. And those two oxygen atoms can produce, once broken, you can have them rearrange and form oxygen gas, as well as the nitrogen can react and form nitrogen gas in an explosive. And you produce all these small gases from this material, and that's what actually fuels its destructive power. So the key thing here is that good Lewis structures tell you something about the substance itself. So don't, memorize, apply. Let's see. One last thing that I want to talk about is then using our units, our polyatomic ion units, to then write correct formulas for salts, as well as naming them. So hopefully this is general review, but say we can take any ion, right, and say we want to write the formula for bringing sodium ion and phosphate ion together. Of course, there should be 3 sodium ions for every 1 phosphate, right? And so the formula correctly written is Na3PO4. And of course, the name would be sodium phosphate. But this is why it is so important to know our polyatomic ions, because we can just simply look at the structure and immediately recognize that this substance is ionically attracted. Of course, inside those bonds, there are covalent bonds, right? Inside the phosphate, there are covalent bonds, but overall, there's this 3 negative charge, and within this crystal lattice, we'll have these alternate with sodium ions around it. And so, therefore, as a whole structure, it's a salt. Till next time, Crip.